And with that, hello everybody, welcome back to a new video. Today I thought I would show you an instruction or an introduction to KiCad. For those who doesn't know KiCad, KiCad is used to make PCBs. In German we say Elektronikplatinen oder Leiterplatinen. But in English it's PCB, printed circuit boards, exactly. And it's a part of our firm, what we offering or making for customers, PCB-Design, exactly. And I thought it's this topic, PCB-Design, is a little bit too unknown in the world. I think how many people know PCBs or PCB design? Nearly no one. For everybody who doesn't know these types of topics, just thinks, oh shit, that's such a printed circuit board. Oh my god, what does it do? Head is exploding, right? But with today's introduction, I will just show you a little bit how these printed circuit boards are made, how you can design such printed circuit boards, etc. pp. We don't go into details here because this is also a tutorial for a complete course. So I just show you the overview, and I will speak what comes me to mind. So I don't have a script or something else. I just want to show you. So you can see here, I have now opened a project here. I think I open a better one for you, to have a little bit more on the PCB. I think I go here. I need to start from nothing, I think. We go into KiCad here. KiCad, currently in the version 8.0. Newer versions are already available, but 8.0 runs fine to me. So this is KiCad. This is a complete tool for PCB design, and it's completely free. There are very expensive paid versions. I think how is it named? I think Autodesk, from Autodesk, there is one. The name, I don't know the name right now, but these types of programs can be many thousands of euros or dollars. So they are very expensive, but KiCad is open source, so everybody can program and watch the code from this program and can develop it. And KiCad is really, you don't have restrictions, because you can see that later when it comes to how to design a footprint for a desired component. In KiCad you can just make it. In other tools where there are paywalls and something else, expensive paywalls, you need to rather pay or don't have the ability. But in KiCad, I've never run into some issues. It doesn't have simulation, so you can't simulate the printed circuit board. But I think for me, it's not a problem right now, because you need to know what you just do. Exactly. So this is KiCad, and like every printed circuit board, it's nearly the same process. We begin with a schematic, an electric schematic, exactly. Because I've opened the wrong one, sorry. I forgot it. Here you can go on project open. Then you can choose your project. For sure, when you at the start you don't have a project, so you need to create a new one. We go now here in, I think we go here, exactly this one here, So you can click it, then here it loads all the files. So, and this one here is a schematic, or here you can see Schaltplan Editor. Exactly. So we go here in the schematic, we open it for sure. So, and now it's, what the Slow down, I will explain it. Okay. For sure, when you start, you have nothing. So you need to first know what you want to do and what is the purpose of your printed circuit boards. For now, in the schematic, it's completely, you don't need to worry about, oh man, how is this looking in the printed circuit board, etc. No, it's just the schematic, the electric schematic. You can imagine that in that way, you have, if you take water, you have water lines, and the water takes a path, or you want to create a water path for your home or something else, and you just you need to create a plan first to where the water runs, where it splits, etc., etc. Where it is a little bit restricted, or where it needs to be high pressure or something else. And just like that here. So you just need to, in reality, you have probably IC chips that are integrated circuits that are just so tiny little chips you saw in my tutorial, in my unboxing. This is just, they have, it would go into much detail here, but they are really small and have a lot of functionalities in it. Just high-tech machines can do or create some of these IC chips, and today they are very developed and very modern. So the IC chip we use here, as you can see it here in the schematic, is this one here, the BQ25756. I can just show you the schematic of this one. This is from Texas Instruments, exactly. Here you can see it. This is also 25. So this is also a process. You will choose your IC because there are very different suppliers for the probably nearly the same IC or the same functionalities, different ICs, exactly. And at the startup, you will need to worry about that, what ICs you choose to suit your application. And if you then have a correct one, or you think, that IC is well suited for my application, you can go here. Probably you go to the data sheet, or you already read it, because the data sheet explains you, it's just like a cheat. So the data sheet is really, here you can see 85 sites of just documentation about this IC, how you need to use it on your PCB or schematic. So you can see it here. I will just go here slowly. Here on the first page, the key features, so what this IC is doing. So you can see here, this is now a bidirectional buck boost battery charge controller. So you can charge batteries with it. What types of batteries? Here you can see lithium ion, or I don't know this one, but other batteries. Also, I think also lithium based. But the lithium polymer, or I don't know. That you can see here. Then the frequency which it runs, the input voltage, the output voltage. So here, wide battery voltage operating range up to 70 volts. So when you have a battery pack, you can charge it or choose to charge it up to 70 volts. If your battery pack exceeds or is 100 volt, you can charge it to 100%. Exactly, just to 70%. Now in this case here with 70 volts. But on the first side there are very overviewed descriptions. I will just make it a little bit bigger for you. Then here you can see the chip's pin configuration. And this one here is now really big on the screen, but as you saw on the tutorial, this is probably such big here. So it's really tiny, and you can imagine how tiny these little pins here are. So here with the numbers, that are the connection points. So that is the copper, or what else, where the electrical current is running through. And you can imagine how tiny these things are. That are modern chips. Modern chips, they are so tiny as possible, and that's good. This is now also a surface mount chip. So you can imagine the chip is mounted just on the circuit board, so it's placed on it, and it's soldered just on the surface, on the top of the circuit board. Few years ago, there are THT through-hole components commonly used. So that are if this one here is the PCB, this one would go through the PCB, and you solder it on the other side. So you solder it on the other side, yeah. That is taking much more space for sure, because the other side is also have a hole in it. So yeah, SMD surface mount components are much better and much tinier and much compact, yeah. And then you can see here, you can see the numeration of the pins. That one will be then important for the PCB itself. So you then place the chip on the PCB, or you make a footprint for it. We call that footprint the place where this chip here is going on the PCB. Yeah, and we need to know then what the numeration of these chips, or yeah, where the pin is, where the pin 1 is, and what function it has to mount, to correctly draw the circuit correctly. Yeah, exactly. And here you have a description on all the pins, so you need to read it. You can't go, there is no shortcut. Absolute maximum rating. So you can at the beginning there was standing I think 70 volt input voltage here, but what you can read here is 85 is the absolute maximum. So if you go beyond the 70 volts and put 80 volts on it, there is still a chance that nothing happened. But if you exceed this 85 volt, then I think nearly guaranteed that something will break, yeah, or the chip doesn't work right, yeah. So as I said, you need to go through here many threshold voltages. You don't need to know this all or to read this all. Much of it is just you don't need anything. So I've also not I've go through it over it, but I don't took here that one here. Oh my God, what's this did? Okay, no. Yeah, you just need to know the things you need to worry about, and you become a feeling of that what you need to worry about. So here you have graphs, etc. Then again, here what it looks intern, so in the IC chip itself, etc. pp. You need to read it, you need to understand it, and then you can draw the schematic. I don't want to go any details more. So here in the schematic, then you will make or import this chip. Yeah, probably there is already one you can just take. So the exact chip we just saw, so this BQ25, etc. And then you can load it in, or you need to create the own one. So in that case here, that it's not very, you just make here a I don't know, here such a rectangle, made the amount of pins it has. So from 1 to I think it's 36, etc. Here's the last one. And you don't need to worry about the footprint. That's just the schematic. This is just an abstract function, description. Then you can load it here, put the pins with the correct functionalities, and then you can read the data sheet, and then you can draw the schematic. So here you can see input, a source here. So here you give the input voltage on it, so probably 70 volts. The 70 volts goes then in there and is powering the IC chip, etc. And here you have much more things, capacitors, etc. And these capacitor values are all described in the PCB schematic, in the IC chip schematic. Yeah. So you don't need to figure or calculate this by yourself. You just read the data sheet of the chip, and there it stands. Okay, listen, 4.7 microfarads. Capacitor, ceramic capacitor, at it needs to be 10% precise. So 10% means this 4.7 microfarads, you don't have exactly those 4.7. There is a little bit of a upper and lower limit where it can be, and in this case it's 10%. So plus minus 10% of this value here, it needs to be. And you can imagine if a component is more precise, it gets more expensive. Yeah, exactly. So then, as I said, I don't go into any details here. Just you will use the data sheet, place all your components, make the schematic, and then you should have a complete schematic of your application, what should work. Yeah. So, but this is a really long process. So I think for this one here, with all the changes and not understandings which I had, I don't want to lie, I think, yeah, 3-4 days of work is normal. Yeah. So you need to read the data sheet. Firstly, you don't understand anything, and then you will choose your IC chip. Then you will start with making these things, and then changes. I need to make changes, etc. This will take a while. This is a process. You will go step by step, and yeah, after hopefully a short time, you will be finished, and you have something like this here. Yeah, exactly. So the next step is then you can convert or no other. You need to. These are just components, schematic components. So yeah, but now you want to convert it into a PCB. So in a real PCB with real components. So you need to choose your components. This is also a thing that will take a while. You need to, for sure, or for example, this 1K resistor here. This is a resistor, 1%. You need to choose exactly a precise resistor or a variety of resistors. Yeah. But it needs to be 1K and 1%. And then you also need to know how big the resistor is for your footprint. Yeah. So the PCB needs to be exactly made for this resistor that you can mount it on and solder it on. Yeah. And for that, you will give here a footprint. This one here. This is not a footprint here. 1206 exactly. SMD. So it's a surface mount. Exactly. And yeah, you need to pair these footprints with your components, and you need to do this for any component. I can just open here. Here you here you have a complete list of all your components in the schematic, and you can go through it and say, okay, this component, that footprint, and you do that for all of it, for all of the list. Yeah. It just needs to load a little bit long, I think. In the meantime, I will just do as I will sing. So you are bored. Probably this is cut out by Nicholas, but I think if he is nice, he will leave it in, and you can hear me singing a little bit. Yeah, there we are. Okay, so here, this one here you can see this is the complete overview of all components. So 119 components. Yeah, good luck pairing them with footprints. Here you can see I've placed here the footprint. Then you can go here and exactly you can show it here. That is the footprint. Yeah. So that here are the exact. I can measure it here. That is the footprint for the component. So your component, there are all listed. So there aren't special components. Every component has a size. So 1206, for example. Yeah. These are normed sizes. Yeah. So you can see here, this component is 1206. So 4.6 millimeters wide, long, and 2.3 millimeters wide. Exactly. And you need to choose for any component that footprints. Yeah. Okay. And when you have done that, you can go into schematic. I've now already have a complete schematic, but when you convert this, you can then just click, I think about here, just convert all the components with the footprints into a schematic. Then you come here in this site, and the components are just, all over the place. So you will then place them here on the side, I think, everyone, and then you will start to drag them in. So you decide where the main chip is. So probably here, this one here is the main chip. You just saw the data sheet of it, this one here, as you saw here, or as you can just see, the similarities that you that it makes clicks here, that one here, is that one, for now you know, so you just decide, so you take that that footprint and place it exactly here, and then you need to worry about distances. So you can't place here, for example, this one here, it's also a capacitor, one of many capacitors. So you can't place them, I don't know, 20 centimeters away. So you can do it, but for the signal, it transports, it don't be good. So this is just one of many things you need to worry about when you make the design. But this is also standing in the data sheet of the chips. So there are guidelines. So hey, don't place this component too far away, etc., etc. So you just make the design. This is now the bare design itself, the PCB design itself. This one here is really, you can see it here. I have a big amount of free space. This is just a prototype, so I've changed it then after just a prototype. So I leave enough space, exactly. And you place it. Then after you place it, you need to make the connections, the copper connections that are here, the red ones here, or you can see it here. Here, that one here is a connection. That's then a real copper connection. So where the electrical current is running through. And as you can just imagine, these parts here aren't that big, or so this chip. So you can imagine how thin this line here is. That's really nothing. I think when I go here, you can see it here. The width of this trace, of this PCB trace, is 0.254 millimeters. So not even a millimeter. It's it's crazy when you think about it. So but for signals, this is enough, because in signal lines this isn't much current which is running through them. For higher current lines, or higher current paths, I need to say, you can see this one here. So this also rectangle. This one here is really big. I can measure it here for you. That's for high current. So probably at this point here, I've designed it for here. This is 10 millimeters, so 1 centimeter, and this is really for high current. So high current, I think, what can go through here? I think 20 amperes, something like that, or even more. It's also depending on the thickness of the copper. But this goes into much detail. So you just design it, make all the traces, and then you have such a design here, such a PCB. You can also visualize it in KiCad. So I've told you, this is a really good tool here, program, and it's free. It's crazy. And then you see this one here, a 3D animation. So you can see the real components here. Here, this chip here is not imported. You need to take you can download the 3D model of it and then import it. And then you have also a model for here. But it's a prototype. I doesn't do it here. So but here, for those components, they were already a component, a 3D model, so you can see it and it will be visualized. So this is the PCB, how it will look like in the real world. Yeah, and then when you finished up with everything, you can take that PCB, send all the files to the manufacturer, probably in China, because there is this is really cheap there. Yeah, and you can order the PCBs, order the components, solder it on with a solder station, and yeah, you have your PCB. This is just a short overview, 25 minutes, so you can imagine how complex these things is. I think I also just know a little tiny bit of what you can do with these things, and I've also worked with a little tiny bit of chips and components. So there is, yeah, there is a lifelong period to learn, and yeah, and you with every project you grow on this types of things, and yeah, it's also a nice thing. It's also, yeah, I love it. I can say that, and I hope with that introduction, I can probably make up a fire in in your in yourself for fascination of this PCBs or PCBs design. Yeah, and with that, I don't want to talk any longer. Thank you very much for watching this video. If you want, please like the video or comment it. It will help me a lot. And yeah, I'll see you in the next video. Thank you.